So some final special topics with regard to thermal response testing. First of all, we can of course do a multi-pulse test where after the first test with a constant heat injection rate, we have further tests with other injection or extraction rates and then also the recovery. We can use this, for instance, to analyze the effects of groundwater flow, the theory being that the higher the temperature, the bigger the effect of the groundwater flow on the test result will be. So we get a non-constant thermal conductivity estimate. You can see this in a little table on the right, where the reference value without groundwater flow is around 2.1. And with the groundwater extraction experiments, we can see that it increases from the first pulse 2.03 to the last pulse about 2.3. This was a test that we performed where the same borehole was forced with the same power rate, but a nearby groundwater extraction well was used to turn on and off the groundwater flow affecting that particular borehole. Another possibility is to test different configurations. For instance, not a vertical borehole heat exchanger, but perform a test on a slinky type, ring collector type heat exchanger. You can see a picture here of a test that we performed during a European research project in Perugia. And then, of course, we can take a look at how a slinky or ring collector type heat exchanger performs. Other possibilities, this uses fiber optic distributed temperature sensing to measure the heat, the temperature response of the ground at different levels. You can see the little black curves that are the fiber optic measurement cables. We can also use this in a typical vertical borehole and get an estimate of the vertical distribution of the thermal conductivity. We can combine this with a classical thermal response test, being a borehole heat exchanger where the fluid is circulated, or we can use it with a heating cable, but with the heating cable, obviously, we don't get any value for the borehole thermal resistance. An example here, you can see on the left the relaxation, so the recovery period temperature profile, and on the right the thermal conductivity estimated from a test with a heating cable and a fiber optic temperature measurement at different levels. And you can see actually a couple of spikes of high thermal conductivity in the profile and a relative average thermal conductivity in the remainder of the profile. So this will give you very interesting results, especially if you have more contrasting geology difference between the thermal conductivity in different layers in the ground. Another possibility here is a test with an actual borehole and a fiber optic measurement in the borehole itself. So we're circulating fluid and then measuring the temperature response at different depths. You can plot that in time and get, let's say, a kind of animation of the temperature evolution in time. In this case, you can also see one of the problems with such a test procedure, because the difference between the different layers here is actually whether the fiber optic cable is very close to the U-pipe heat exchanger leg or a bit further away, which affects the temperature that is measured. So the analysis of this type of data is relatively complex. The thermal response test, it's been used for over 30 years in over 30 countries, and it's been very useful in many cases for getting an idea of the thermal properties of the ground, for getting an idea of how a system can and will operate in practice. A lot of research has been done, really an enormous amount of research has been done in the past 30 years. And this list that we show here is only a very small selection of that big bibliography. So if you want to know more, Google for in situ thermal response test and you will find a lot of references.